So, good afternoon, everybody. And for starters, I would like to say that it is really fortunate that I have the opportunity to be here today and simultaneously learn new things and be able to share what I am passionate about. And I think we are all really, really lucky today. And so allow me to introduce or reintroduce myself. My name is Daryna Aihars, and I am a physics student and enthusiast at the Chernihiv National University in Ukraine. And what I'm talking about today is the modern approaches to solving the problem of the sonic boom in supersonic flight. Yeah, complicated. The simpler way to put it is the planes that fly at the speed of sound, the problems that we have with them, and how to solve it. And first of all, what piqued my curiosity is that supersonic technology is used a lot in military, in science, as experimental aircraft. But I asked myself a question: why did the engineers in the 80s or 90s think that it is a cool idea to actually make such aircraft carry passengers? And now I'm going to translate it to you. Imagine that you can actually fly from New York all the way to Paris in just 3 hours. Needless to say that you can also make it from Budapest to Paris, for example, before anybody can finish their lunch. That is super great, right? So actually, it used to be possible at some point in history. Thanks to the Concorde, the French aircraft, I have a smaller and cuter version of it right here. You can see it has a peculiar shape. It's for the physical reasons. And it flew for 27 years before being permanently suspended, and the engineers deciding that they are not doing the supersonic passenger flights anymore. And you might ask yourself why, and I am going to answer. There are 3 fundamental reasons why the supersonic flights for passenger-carrying aircrafts are not really possible right now. The first 2 of them are the environmental impact and the fuel costs. Those are a little outside my scope of research, but there are a lot of publications on that point, and you can keep up with them if you are interested. And the third fundamental reason is the disturbance of peace that it causes for the locals. You can see it right here that the aircraft has some sort of a skirt or a dress. It's really stylish. And that actually happens when the aircraft breaks the invisible sound barrier. So imagine that here, once the aircraft flies through this point, it is flying faster than the speed of sound. And fun fact, it may also be called the Mach speed. So for example, if you see that the aircraft is flying at Mach 1.4, it means that the aircraft is 1.4 faster than the speed of sound. And once it reaches this threshold, something weird happens, because the physics works differently when the aircraft is flying at supersonic speeds. It bends around the nose, it builds up the pressure waves, and they do not even out throughout the sky. They build up here at the nose, and they build up here at the tail. And when they combine, they build an N-shaped wave that spreads throughout the sky and until it reaches the ground. And I made a Python simulation of how it works. It's a little laggy, sorry, but I think you get the point. You see that it spreads towards the ground. And the problem is that once it reaches the ground, it sounds really loud. It sounds like an explosion. And in some extreme cases, some windows are breaking. And of course, imagine that you live beneath the Concorde airway, and once it's flying over you, your windows are breaking. Of course, you're not happy about that. And therefore, scientists are working on a solution on how to battle that. And right now, there are 2 fundamental approaches to how we can make this a little better. We cannot make the sonic boom disappear, because that is a limitation put on us by Mother Universe. We cannot fight the physics, but we can manipulate them. And therefore, the ways in which we can make it better are, number 1, reshaping the boom, and number 2, redirecting the boom. And so the first solution is a really, really long nose. And I'm being serious right now. Look at this. Look how interesting they look. Those are real aircrafts being developed right now. The first one is the NASA aircraft. It is experimental, and it is specifically being developed to test the technology of battling the sonic boom with the shape, of being able to reshape it, because the boom still exists, but it's not really a boom anymore. It's more like a thump when it reaches the ground. So no windows are breaking anymore, and people are not that concerned. And the second one is an experimental passenger-carrying aircraft, but we do not know when it's going to exist. And the second approach is the redirecting approach. And look at this. This is another graph that I simulated. And this, for example, represents the waves. And here is the bad case scenario. They reach the ground. And this is the perfect case scenario, because you can see that at this point, they refract and they bend upwards. Why does this happen? This happens because of physics, and physics are incredible. When the aircraft flies at a high altitude and faces dramatic changes in temperature, pressure, and the winds, the wind parameters, then it can actually cause the pressure waves to get slower. And when the waves get slower, they want to go upwards. They are wired like this, and that is good for us, because it means that we can actually find the solution to this very, very specific problem. And what the research is about is for me to calculate the conditions that need to exist for the Mach cutoff. And specifically, I'm observing the area in Western Ukraine, since that is where I live, and calculating how many favorable days there exist for the Mach cutoff to happen. And imagine what is going to happen once we combine the reshaping and redirecting, and once a model is developed for automatic calculation of how favorable it is for the Mach cutoff to exist. And that is exactly what I'm aiming to develop with my research. So I was extremely happy to share this with you. If you have any questions, I will be pleased to answer. Sincerely yours.